another form of differential equations. Like I said, we started with this form. M a function of x and y dx plus n a function of x and y dy equal to 0. Right? Now suppose, so there are times when this expression could be written as a perfect differential. M dx plus n dy, there are times it could be written as a perfect differential, d of phi. M dx plus n dy could be written as d of some function of x and y. Some function of x and y. It'll not always happen. It'll happen sometimes. And whenever this happens, when this can be written as d of phi, then this is called an exact differential. This is called an exact differential. This is called an exact differential. Okay. Say x dy plus y dx. Do you realize this expression is d of xy? It's a perfect differential. It's a perfect differential. Yes or no? It's a perfect differential. So if someone says x dy plus y dx is 0, you would say d of xy is 0, xy is constant. That's the solution to this differential equation.
So may I please ask a small question? So yesterday itself we were discussing that, when we are calculating a differential, we are essentially looking at 0 by 0 at a particular instance.
Derivative, not differential, a derivative.
A derivative. So sir, just asking, we do use this for problems, x dy plus y dx, we are shortening it as dxy. But with respect to nothing,
It's a change in xy, yaar. What it means is, this is how you want to read this. X into a small change in y into a small change in x is a very small change in xy. This is what it means. D is a change here. D is an infinitesimally small change. So if you have two variables and you have changed x by a small amount dx and y by a small amount dy, then xy changes by an amount x dy plus y dx. This is what it means. No, why, yaar? I mean, if I say your age has increased by 1 year in the last 1 year, what is relative about it? Huh? Is the time interval it took for you to reach this place from home was, say, few hours. Now, what is relative about it? Huh? You have 20 mangoes and you add 5 mangoes to it. What's the change in the number of mangoes? 5. What is relative about it? Right? A change is a change. Right? In this case, a simple change. So this is like d of phi equal to 0. Say, I could have also had x squared cos y dy plus 2x sin y dx, for example. Look at this. Look at this. This can be written as x squared d of sin y. Cos y dy is d of sin y plus sin y. 2x dx is d of x squared. Is it a perfect exact differential? Is it not d of x squared sin y? This is sin y. X squared sin y. Is it not d of x squared sin y? It's a perfect differential. It's a exact differential. It's a exact differential, right? And it will not happen always. M dx plus n dy is d of phi, will happen sometimes. And as and when it happens, This expression is called an exact differential. It's called a exact differential. These are the best problems to solve. They are easiest. Right? Easiest. But the point is, if you have a horrendous looking mdx plus ndy, and even before you venture into figuring out or using exact differentials, you should know whether it's at all possible or not. You should know whether it is at all possible or not. That should be known to you, right? Now, the proof of what I'm going to say is really beyond the scope of this class at this point of time, but it will help to know. To know whether this is a perfect differential or not, that is mdx plus ndy could have been written as d of phi, some function of x and y, right, in general. The test to be performed is the following. In the event it will pass this test, you know that it's a perfect differential, and you will have the courage to express it as a perfect differential. Go ahead and perform some manipulations to express it as a perfect differential. Now the test is as follows. This is m, this is n. Differentiate m with respect to y, keeping x constant. Dou m dou y is what? Derivative of m with respect to y as if x is constant. And then differentiate n with respect to x, keeping y constant. Dou n dou x. Differentiate this with respect to y partially. Differentiate this with respect to x partially. And if this turns out to be equal to this, then it will be an exact differential. Then it's going to be an exact differential. If dou m dou y is dou n dou x, it's going to be a perfect differential. Check that out. This is m. Differentiate this with respect to y, you'll get 0. This is n. Differentiate this with respect to y. This is y. This is x dy plus y dx. So m with respect to x is going to be 0. If you differentiate y with respect to x, it's going to be 0. If you differentiate x with respect to y, that's going to be 0. Yes or no? Right? Which means that's the reason it turns out to be an exact differential. Differentiate this with respect to y, 1. Differentiate this with respect to x, 1 and 1, both. I'm sorry. You know, this is m dx plus n dy. M to be differentiated with respect to y. That gives me 1. N, you want to differentiate with respect to x. And that will be 1. So 1 and 1, they are equal. So it's a perfect differential. Look at this. 2x sine y. Differentiate this with respect to y. You get 2x cos y. 2x cos y. N dy. Differentiate this with respect to x. You get 2x cos y. They are equal. That's the reason it's a perfect differential. Do you all understand what I'm saying? So if dou m dou y is dou n dou x, if dou m dou y is dou n dou x, it will be a perfect differential. You don't have to bother about any of the forms. Just recollect terms, rearrange terms, and you'll get it as d of phi equal to 0. Phi equal to constant would be the solution to that differential equation, right? Now, let me give you an example. Check this sheet, problem sheet. X squared minus ay dx minus ax minus y squared dy equal to 0. So this is like x squared minus ay dx plus y squared minus ax dy equal to 0. This is my m and this is my n, right? I want to check whether it's a perfect differential or not. So I'll take dou m dou y, differentiate m with respect to y, I'll get minus a. And I'll differentiate n with respect to x, Dou n dou x, that's also minus a. The two are equal. This therefore must be a perfect differential. This therefore must be a perfect differential. Good. Now, what I do is, I write terms as x squared dx. This is x squared dx. Y squared dy. And then minus a into y dx plus x dy equal to 0. This is what I do. Yes or no? Right, right. This is d of x cube by 3 plus d of y cube by 3 minus a d of xy equal to 0, right? This is like d of x cube plus y cube by 3 minus d of axy is 0, right? So this is like d of x cube plus y cube by 3 minus axy equal to 0. So this must be constant. So the solution to this differential equation is x cube by 3 plus y cube by 3 minus axy equal to constant. I'll tell you a shortcut to an exact differential, but don't, whatever shortcut I'm telling you, don't deploy in your board exams or school. All right? If you've figured out that a differential equation is exact, that means dou m dou y is dou n dou x, I'll tell you, for the sake of getting the answer, what I'm going to tell you will work unconditionally at all times. Listen to me. But don't use this in school or boards. Right? But you understood, you know how we did it from first principles? Rearranging terms. I had the gumption to rearrange terms because I knew it was exact and it will boil down to an exact differential. Right? Now what you can do is, first write down. Integrate m with respect to x as if y is constant. Integrate m with respect to x keeping y constant. Integrate n with respect to y keeping x constant. Integrate n with respect to y keeping x constant. Okay? You integrate this with respect to x as if y is constant. Integrate this with respect to y as if x is constant. Now, write down. After having done this, if in the two integrals, there is a common term, then it should appear only once. The solution to the differential equation would be the sum of the two integrals, ensuring that the common term, if at all, common term or terms occur only once in the answer. Common term or terms occur once and only once in the final answer. See, I integrate this m as if y is constant with respect to x. right? What do I get? X cube by 3 minus ay into x. Now I integrate this. Y squared minus ax dy. I get y cube by 3 minus ax into y. This is a common term. In the final solution, this plus this, but with the common term appearing only once. So then the solution is going to be x cube by 3 plus y cube by 3 minus axy equal to constant. That will be the solution. That will be the solution. Is it the same? Yes. That will be the solution. It will always work. Don't use these stunts in school. Okay? It will always work. There, axy, for example, in some cases you will not find a common term, then just add. If there is a common term, in this sum, it must appear only once. That will be the solution to the differential equation. Equal to, huh? एक बार आएगा, right? Let me illustrate a little more. Huh? Huh? Of course, yaar. Of course, there is a proof. All right. Let's solve it the normal way first, but let's figure out whether it's exact or not. Right? This is my m. This is my n. So I'll say dou m dou y. Dou m dou y is what? E power y cos x. Yes or no? And what is dou n dou x? Dou x dou e power y. ये क्या था? Sin x था? Must have been sin x, na? Sin x. Dou n dou x is going to be e power y cos x. Yes or no? It's a perfect differential. It's a perfect differential. So let's first solve it the legal way. Right? Legal way. All right. So this is like e power y cos x dx plus cos x dx, right, plus e power y sin x dy. Okay? Club these two. So this is e power y d of sin x, cos x dx is d of sin x, and this is e power y dy is d of e power y, is e power y dy is d of e power y. So plus sin x d of e power y plus cos x dx. Cos x dx is d of sin x equal to 0. Right? What is this? Derivative of the product of two functions. So this is what? Derivative first into second plus derivative of second into first, e power y. Right? So this is like d of e power y sin x plus sin x equal to 0. Yes or no? So e power y sin x plus sin x must be constant. Must be constant. That's the solution to this differential equation. Now let's do the ulta pulta thing. The solution is e power y plus 1 into sin x equal to constant. That's the solution to this differential equation. Right? Now let's go the illegal way. Integrate m with respect to x as if y is constant. Integral e power y plus 1 cos x dx as if y is constant. What would this be? E power y plus 1 sin x. Integrate this with respect to y. as if x is constant. So that's like e power y sine x. Now, e power y sine x, e power y sine x is a common term. So when you add these two, that e power y sine x must appear only once. So the answer is going to be e power y plus 1 sine x will be the answer. Because when you add these two, na, e power y sine x, e power y sine x cannot appear twice. That's a common term. So e power y sine x, this will be the answer. When you add these two, don't add this again because this is already come in here. So the answer is going to be e power y plus 1. It'll work. Word of caution again. Don't do it in your boards. Don't do it in your school. But this will always work. Okay. So that's the business of exact differentials. That's the business of exact differentials, where, you know, if dou m dou y is the same as dou n dou x, you know it's an exact differential, and you can venture into solving that, expressing that as a perfect differential. It'll work. Okay.